Well, it's April 5th, 2012, and we come to another place that's familiar to me and to Calvin Castine behind the camera for Hometown Cable, and that is the Woodman Lodge number 462 on the dead-end Macadam Road in Chazy. It's a great spot. We've had so many wonderful functions here. It's almost like home just to come back here. And to meet Dr. Ray Johnson. How are you, Ray?
Very well, thank you. Thank you for
So
inviting me.
pleased to meet you. Even though I've known who you were based on your photograph in the paper all the time, I don't think we've ever formally met.
No, I don't think so.
Well, that's because the climate hasn't changed enough. How are you really?
I am doing well, thank you.
Do you live in this general vicinity?
I live in Chazy, yes.
Not far. And you worked for how many years at Wyeth?
I worked for Wyeth for 30 years in Rouse's Point.
And, you know, I always look for common ground when I shake a hand, and I come to find out you did spend some time, like 3 years, in Pearl River, where I was born.
Right.
Many people here know that it's the home of Letterly Labs for how many years?
Long time.
Long time.
Yeah, long time.
But that's not where your career started. You were born and brought up in Brooklyn.
That's correct.
You've almost lost the accent, but you haven't lost the Brooklyn edge. Because you've traveled a bit since then.
I went to school at Clarkson and then came over here, and this was where I started work for Airst at the time in 1969. And we enjoyed the community, and we brought our family up here, and we really enjoyed it. So when I retired, I wanted to come back home. This is home to me.
You know, this home to a lot of people, and it feels like home to me. As you said, you must be a native by now. I've been here since '61, but in actuality, I used to work on an air base when they built it, on construction in the early 1950s. But how did you end up at Clarkson?
They had a graduate program in chemistry, and I was offered an assistantship that would pay for my tuition.
That works. That works.
That was a real good draw for me, and my experience there was very positive, and I enjoyed my stay there.
You know, that's another thing we have in common, except that you made it through Clarkson and I didn't.
Oh.
I wanted to be a civil engineer at some point in my life before the radio bug bit me. So I went to Clarkson for a year as part of my career and ended up at Stony Brook on Long Island. So do you have relatives back in Brooklyn?
Yes, my brother still lives there with his family, and my sister lives there with her family on the Queens side of the border. So yes, we still have family there.
Still a great borough. It's an iconic borough because so many things happen in Brooklyn.
It's changed a lot, and I think it's a lot more culturally diverse than it's been in the past. And I think there's a lot of very interesting ethnic groups there that bring a lot of character to the city in terms of food, in terms of culture.
I always loved that even as a small child. My father had that sense that he would take us to these wonderful restaurants in Chinatown and Harlem and Brooklyn. And of course, spending childhood at Coney Island wasn't bad either.
Right. You must have eaten Nathan's hot dogs.
Oh, Nathan. I remember the old commercial, let's go down to Nathan's for a red hot Frank. I love it. Lots of great memories. So it's amazing how we end up where we end up.
We do, that's true.
And why did you have an interest in the sciences as a little kid in Brooklyn?
I did, actually. Matter of fact, when we were working on my mother's house, I ran across some books that I had from the 1950s and that I used to read and enjoy. So I've been interested in science really my whole life.
There are a lot worse places to work than Wyeth, and a lot of worse places to live than this portion of the North Country. So I'm glad you came here. Before the cameras began, we talked about your kids. You had 2, 3?
We have 2 daughters.
2 daughters. Both went to local schools. One to Northeastern, you said, and one to St. John's.
That's correct. Yes.
And they both live in this area?
Our younger daughter Sarah does with her family, her husband Tom and 4 children. Our other daughter has just moved to Hartford, Connecticut, where she lives with her husband and 2 children.
That's amazing. I think we've covered the whole family thing. Why climate science? The people who are familiar with Dr. Ray know that you have been writing for the newspaper periodically, what, once a month now?
It's once a month, first Sunday of every month, and I've been doing it for over 3 years now. So I've got about 38, 39 articles that I've written for the paper.
I've done almost 800
Well,
and would have started earlier, but I was too busy in the radio business till 1997, and so that's when I began a weekly column, and now it's every other week.
okay.
But it's not nearly as scientific or erudite as yours. It's what kind of coffee do you drink? What diner do you? The last couple have been about North Country diners, and I opened up a Pandora's box of people who remember diners that I never heard of, but that's fun. So, did you approach them? Did they approach you? How did that marriage begin?
Well, I approached Bob Grady at the time at a function in Plattsburgh, and I mentioned to him that I thought that it might be useful to the local community here to have the science presented without politics and without opinion, just the science, and let the data speak. And so he asked me for a typical column or a draft column, which I sent him, and he found it agreeable, and so that's how it began.
Isn't that amazing?
Mm-hmm.
Well, it started with me with a free lunch, because I'll do anything for a free lunch. So do you get good reaction?
I get.
I've read many hundreds of the comments of your column, and they run the gamut, don't they?
They do run the gamut. Some are positive, some are totally negative, and some are questioning. So it does run the gamut.
You have to have a thick skin if you're going to be in this business.
I'm developing one.
Are you really?
Yes.
You try to please everybody, but it's impossible.
I guess there's two sets of comments. One that I get that is from a skeptic who is not sure about the data or who has been presented with other data that is at odds with the data that I present. And that I can understand because if they have some information and it doesn't jive, they're a little confused about it. There's the other type of comment, which is a total denier type comment, and that's the one that I personally have to really get over, because if I present data from 4 countries on temperature around the world and it all shows global warming and a person says it's not warming, there's not much I can do about that.
You can go back 50 million years and pretty well define it, but at the present time, some people, they have biases.
Yes, they do.
And you mentioned that early, you try not to bring in the religious aspect, you try not to bring in the political aspect, just presenting the science. But sometimes you might get on that fence and threaten to fall off one side or the other, Doctor.
Well, I think that's very true, because I perceive this as an issue that is going to be one of the most critical in the 21st century. And I have grandchildren, you have great-great-grandchildren, and really that's why I'm doing this, because this isn't really going to impact me over the next decade or whatever. It's really going to impact the future generations. And the issues that I perceive coming out of this are very severe, and we're beginning to see some of the happenings as a result of the climate change that's ongoing right now.
Time takes on a different aspect when you deal with a perspective of millions and millions of years. A little different from the average lifetime of 10 and 75, 80, 90 years. But the science you're talking about had its start a long, long time ago.
Well, I'll show some information here, Gordy, with regard to really climate information that was captured from ice cores in both Antarctica and in Greenland. And the ice cores go down almost 2 miles, so there's lots of information in these cores. And from those cores, they can take a good look at what past climates have been like, and they've gone back about 800,000 years. So for the last 800,000 years, there's pretty solid evidence about what the Earth's climate was like. But in the last 50 years has been the biggest change because of the consumption of fossil fuels, the generation of carbon dioxide into the atmosphere, and the heating of the planet that occurs as a result of that activity.
if I am passionate about reading about some of the latest cores that they've pulled up over the last year or so, you must be ecstatic to see some of this stuff.
The science is definitely getting stronger every year.
It's amazing.
Yeah. Yeah.
Who would ever dream they could go down 2 miles?
There's
And now more, a lot more.
There's a gentleman that wrote a book, his name is Richard Alley, it's called The 2 Mile Time Machine. And it's a fascinating read about how these people under very difficult conditions in the Antarctic or in Greenland, northern Greenland, are able to get these drilling rigs in, capture these ice cores, preserve them so they don't change. They then send them to Colorado, to the National Snow and Ice Data Center, where they're frozen at minus 30 degrees. So then they can be sliced into pieces and then studied. So the science has been just fantastic.
You know, I'm almost too old to be that excited about things, but I don't understand the science nearly as well as you do. But even from a peripheral point of view, it's interesting to the average person, especially since we're doing this in early April 2012. We've just gone through a couple of weeks of temperatures nudging 80 and 81 degrees, and people are calling their friends in Florida and they're waking up to 39 degrees in the morning. And we have a lot of people who grow apples, a lot of people who make maple syrup, a lot of people who just
Right.
farm in general who are very tuned to climate. They have to be. Their livelihoods depend on it.
I think we're beginning to see the impacts, both locally and nationally and globally, on the concentrations, as a result of the concentrations of greenhouse gases in our atmosphere. And as these greenhouse gases continue to accumulate, which they are, and they trap energy into the atmosphere, I think we can expect to see more of this.
It's, you know, I've lived a lot longer than you have, but between us, among the three of us, with Calvin, your youngest in the room, we've seen a lot of changes in technology, but never dreaming as a child that we'd be sitting here with a laptop computer with access to the world and talking about climate change, because it was just, you know, when I was a young guy, oh, it's a nice day.
Right.
It'll be a warm summer, or the caterpillars have 5 stripes, so it's bound to be, you know.
Right.
So here we are in 2012, and you've put together an actual presentation that you said you've made about a dozen times.
I have given talks to various organizations in the community, and my intent again is just to present the science as the best I understand it, and to try and indicate what is happening in our atmosphere and what we can expect as a result of these increasing levels of greenhouse gases in the atmosphere. And I think the Q&As that I've had after each of the talks have been very interesting, because people are very curious about what's going on. And if you listen to the media, you might not always get a full picture. This is not
You're
something...
being so kind. You're being so kind.
This is not conducive to a soundbite. The science
That's
here...
why we're here with that hometown cable camera that just keeps running till Calvin
You bet.
falls asleep back
It's not
there.
a 30-second discussion. It's much more involved than that, and there's lots of data and good information to really support the fact that climate change is occurring.
Let's talk about it.
Okay.
Go right ahead.
All right. Well, basically this talk that with Gordy that we'll cover, and Gordy, please interrupt if I'm not clear about a particular issue, which I'm sure you will. Interrupt me. This is something that I've given to the community a dozen times in the last couple of years, and I try and keep it fresh by adding new information as I get it. And so, as we mentioned, this is the science. What does the data show? And basically, this is a beautiful picture of home, and this was taken from about 22,000 miles in outer space. And the reason I'm showing this is that you can't see the atmosphere in this picture. And yet the atmosphere is where all of our weather and climate comes from. And the Earth is about 8,000 miles across, but the atmosphere is only about 10 miles thick. So it's kind of like the skin on a Mac apple. It's very thin, and yet it plays an enormously important role, just like the skin on an apple plays an important role. This is from the International Space Station, and again it shows a sunset, but you can just see a little bit the very thin skin of the atmosphere that surrounds our planet.
What amazing pictures. Isn't it astounding?
They're
Things
beautiful.
that we can only dream about as kids, huh?
Yeah,
I love it.
we'll make a scientist of you yet.
Oh, no.
And then basically, what is the greenhouse effect? What happens is that the energy from the sun comes in through our atmosphere. It's absorbed in part by the water, by the land, by the air, and then there's an equilibrium where excess energy is released into outer space. And this has been going on since the planet came into being 4.5 billion years ago. What has changed is the atmosphere, this blanket of air around the planet. And as a result of the greenhouse gases, less energy then is released to outer space. So we're not in equilibrium anymore. And so what's happening is that these greenhouse gases are returning some of the energy that normally would be going into outer space back into the land surface, water, and air. That's the greenhouse effect. If you go into your living room and the windows are all closed and it's a bright sunny day, you're feeling the warmth from that energy from the sun, and it's being trapped in your greenhouse, in your home. So it's really a very simple concept, but just to try and explain it a little bit more, the air that you and I are breathing right now, 99% of it is oxygen and nitrogen. That's it. And if you were to take oxygen and put it in a glass tube and shine energy in one end, you'll get all of the energy out on the other end. It doesn't absorb any. And if you do that with nitrogen, same thing. You put energy in on one end, you will see all of that energy coming out the other end. So they're transparent. But if you fill a tube with carbon dioxide or any of the other greenhouse gases like nitrous oxide and some fluorocarbons, if you put energy in, nothing will come out the other end. It is being absorbed. So 99% of our atmosphere is totally transparent to this effect. It's only that 1% that we see on the top there that has an impact on weather and climate. And that 1% consists of a number of different things. The smells from your roses, to carbon dioxide from our cars, to wood smoke. So that 1% is a very small amount of our atmosphere, but it has a very major impact. And what I focus on and what climate scientists focus on is that small amount within that 1% that affects climate and weather. Without carbon dioxide, we would not be here because all of our trees, all of our plants incorporate CO2 through photosynthesis and give us everything we eat, the trees that we see, the flowers that we smell. So carbon dioxide is an essential component. We need to have it. It's just when you get too much of it, like after Thanksgiving, that it's not necessarily good for you. So everything, all life as we know it, depends on some levels of carbon dioxide in order for us to live. In order to try and understand the present and get some inkling as to what the future may hold, scientists have gone to the past, back into the past as far as they can, like we were talking about with ice cores. These are photographs here taken in northern Greenland. The Danes started this project in the late 90s and began to realize that the ice there was up to 2 miles thick. And so they thought, well, if we could go through that ice and take ice cores, that there'd be a story in that ice. And that's exactly what they did. So this particular photo here, or series of photos, shows the drilling rig, an early version of a drilling rig. It shows the cable that holds the the saw blade, if you will, the circular saw blade that goes down through the ice. And then this young lady here is holding the prize, which is this 4-foot section of an ice core. And then they package those up and ship them to a deep freezer, and then they do the analysis. So this was the beginning of looking back into the past to try and understand today and tomorrow. These ice cores now have, both in the Arctic and Antarctic, have gone back a total of about 800,000 years. And they've told a wonderful story, and I'll show that with you in a minute. This is the National Snow and Ice Data Center in Boulder, Colorado, where they store these ice cores, and they've got thousands of these cores, samples of these cores. And they farm them out to scientists around the world to do various analyses. They look at pollen to see get some idea as to what the vegetation was like. They can look at different, what they call isotopes of oxygen, which tells them what the temperature was. In the bubbles of the ice, they can look at the atmospheres that existed 300,000, 400,000 years ago. So they get a lot of information from this. And it's been really, as an analytical chemist, it's been fascinating to me to see how much information you can get from a piece of ice.
Sure. But isn't there open water in some areas underneath those ice covers?
Yes, as a matter of fact.
This recent information has been so exciting.
Yes. In the Antarctic, the Russians have been drilling for about 8 years down through 2+ miles of ice to sample waters of Lake Vostok.
That blows my mind.
And actually, they had to leave a few weeks ago because the winter season was starting. So they didn't have time to get a sample, but they did penetrate through to the lake surface, and they're going to come back next year and collect some of that water and then analyze it. They think it's been unavailable to the atmosphere for about 1 million or more years, and so they think there might be some primitive life forms in there that we haven't seen.
It's beyond the wildest imagination. So for you as a scientist, they must drive you nuts to think, well, I want a drink of that water.
Well, the U.S. is starting on another lake not too far away, and I believe Great Britain is also going to sample another lake. And there are different sized lakes in different areas, and they think there might be different kinds of microbacteria or other microorganisms in the water that might be very primitive and different than anything we've seen today.
It just all adds to our tremendous body of knowledge, doesn't it? I didn't mean to interrupt, but
that's all right.
When you were talking about ice cores, I said, yeah, but there's a lake down there.
That's right.
Go right ahead. I'm sorry.
It's okay. All I'm just showing here is on the right-hand side of that photograph there is a tree, is a cross-section of a tree trunk. And basically what they do in an ice core is sample the ice core and take slices. And each slice is a different year or series of years, just like in a cross-section of a log, where you have the different rings coming back and reflecting different ages of the tree. Same idea. This is interesting. This is a slice of one of those cores, and this is from 1410. So they were able to count the layers of ice back in that core.
Don't you love it? Time machines.
That is a time machine.
Exactly.
And those little bubbles you can kind of see there as light spots, those bubbles are the atmosphere at the time that snow fell in 1410. And so this was an exhibit at the Natural Science Museum in London this past year, and they had photographs, and they actually did have a slice there of a chunk of the ice core. So that's what they do, is they get that slice and they try and date it by counting back and then analyze it to understand what it was like back then. This photograph here goes out about 400,000 years, and basically by doing many times what was in that previous slide, thousands of times, they went back through those ice cores and analyzed them. And they came up with a chart here. This chart has got, it's a little busy, but if you bear with me.
It's very busy.
What it shows is the temperatures and the carbon dioxide levels in the atmosphere over that period of time. Mm-hmm. And it shows a very distinct lockstep of carbon dioxide concentration and temperature. And basically what they found was that As the temperature began to increase due to orbital factors, and I'll have a slide of that in a minute, the carbon dioxide followed closely behind it and was a positive feedback to the temperature. So as the ice sheets began to melt, the CO2 concentrations in the atmosphere began to increase, and that was a positive feedback, which then helped the ice sheets melt even faster. So when you think about it, right here in Chazy, there was 10,000 feet of ice, and yet it didn't take that long for that ice to melt. And that always boggled my mind to think about how much energy it took to melt that amount of ice. If you were down in southern tip of Manhattan, you would not have seen the Atlantic Ocean. The Atlantic Ocean was miles away offshore because the ocean levels at that time were about 350 feet lower than they are today. Long Island didn't exist because Long Island is the result of having the glaciers deposit sand in one place as it moved forward. So the world was very different only 20,000 years ago.
Oh yeah, only 20,000 years ago. Yeah.
I include this here, and I don't mean to get technical about it, but only from the point of view is that the Earth, as it goes around the sun, does not do so in a perfect circle. It goes in an elliptical fashion. And the Earth, as you know, our days are getting longer because of the tilt of our planet. And here you can see the tilt can vary of the planet. And so if the Earth was rotating around the sun straight up like this, our days would be the same length, winter, spring, summer, fall. They'd always be the same length, but it's not. It's tilted. And that tilt brings about energy changes. So if you tilt it a little bit more, that winter sun is not all that warm, as you know, because we're tilted away from it and the sun is going through more atmosphere. But during the summer, when we're tilted toward the sun, you get a lot more heat from that sun. And basically that's the principles of either formation of ice sheets and glaciers, and then the melting of those glaciers depending on the tilt and where we are in the orbit around the sun. If we're closer to the sun, obviously we're getting more energy. If we're further from the sun, we're getting slightly less. So it's these orbital factors that have, in large measure, that account for the ice sheets, the advance and retreat of the ice sheets. This is a very interesting one, and it's in our time, Gordy, in the sense that this was a man named Keeling, Charles Keeling. He was a graduate student in California, and he was given a task by his supervisor to measure carbon dioxide in the atmosphere. It had not been done before. And so that's exactly what he did. He developed a technique to measure carbon dioxide in the atmosphere. And this is the curve over the next 50 years, and this is one of the most iconic curves in climate science. It shows a gradual increase with time of carbon dioxide concentration in the atmosphere. At the time he started it, the concentrations were somewhere around 320 parts per million. Today they're 392 parts per million. So the amount of carbon dioxide in the atmosphere is really increasing. And in addition to that, the rate of increase on the upper portion of the curve here is even steeper than it was back in the 1960s, 50s, 60s, and 70s, because we're consuming a lot more fossil fuel today. For instance, the United States alone burns just about 1 billion tons of coal every year. Today, the U.S. is consuming about 20 million barrels of oil every day. And we consumed that yesterday, and we're going to consume it today, and we're going to consume it tomorrow. So there's been a tremendous increase in our release of greenhouse gases, primarily carbon dioxide, into the atmosphere. So this graph here is one that is referred to a lot. It's called the Keeling curve. And as I mentioned, the NASA and NOAA, the two organizations in the United States that do a lot of climate work, are continually adding new data to this. One of the questions that climate scientists have received from people that are uncertain about the status of where is this carbon dioxide coming from? Is it coming from a volcano or an under ocean vent? And the answer is no. Most of the carbon dioxide is coming from us. And what they did was they actually measured very carefully the amounts of oxygen in the air. Because if you take coal or oil, it's mostly carbon. And if you burn it with a match, you're going to get carbon dioxide. Where does the oxide come from? It comes from the air, just like we're breathing right now. And so what they've done is really look very carefully at the amount of oxygen in the air. And the amount of oxygen in our atmosphere is decreasing by the same amount that the carbon dioxide is increasing. So there's a direct correlation between the reduction in oxygen in our atmosphere and the increase in carbon dioxide in our atmosphere. Direct correlation. This one is another example of the data they got from the ice cores. And again, it shows the glacial periods when it got really cold, and then the warm periods when it warmed up and the ice melted. But what's of interest is that over this long period of time, I think this goes out to like 600,000 years. Over this long period of time, the amount of carbon dioxide in the atmosphere never exceeded about 280 parts per million. So over that long period of time, that was the maximum amount of CO2. And that's reflected here in this curve here. You can see that dotted line across the top. But today, and that's the steep rise here at the end of the curve, today we're at 392, as I mentioned. So within the last 100 years, we've gone from what has been a normal state of affairs for 800,000 years to some new territory. And so we're charting new territory today in terms of our atmosphere.
We're charting new territory for me every time you open your mouth. We're going to pause for just a moment and we'll be right back. Once again, for those of you who might have just turned your television sets on, we're at the Woodman of the World Lodge 462 on the Macadam Road in Chazy, talking with Dr. Ray Johnson about climate change. And when we were off camera, Calvin just asked you a question, and you responded with an answer that I didn't dream of, because I thought CO2 was good for all plant life. And you said not necessarily.
Well, photosynthesis is the process of a plant taking in sun energy and carbon dioxide into its leaf and water from the roots and making more vegetation. And some plants respond very positively to that. They have more oxygen, they have access to more carbon dioxide, so they will incorporate that into their photosynthetic pathway. But not all plants do that. Some of our food plants actually begin to decrease in yield as the CO2 levels go up. Some trees do put on more wood with higher CO2 levels, some species do not. So this is a very active area of research right now to see what will be the impact of increased CO2 levels on our plant life.
You said poison ivy. That everybody's ears in the room perked up, because poison ivy seems to like CO2.
Yes.
Isn't that amazing?
Poison ivy seems to incorporate higher levels of CO2 very easily into its biological processes, and so it tends to grow much faster.
That's great. We're sorry to interrupt.
That's okay.
Okay, go right ahead.
What I was referring to here is the fact that our planet is entering new territory in terms of the composition of its atmosphere. New territory in a sense of the last 800,000 years. 20 million, 100 million years ago, or when the dinosaurs were here, we did have levels of carbon dioxide higher than we have today. But that's when the coal seams that we now mine from our planet were laid down by the vegetation during those epochs. And those coal seams could be anywhere from 6 inches to 60 feet thick, depending on where they are. And that is old vegetation that incorporated CO2 from the air. And as they died and fell in, more grew on top of it, and then the pressures of the earth converted into coal and oil. So in a far back history of our planet, we did have higher levels of CO2. But in terms of human civilization, it has never been this high. And with a planet with 7 billion people on it, and having these high levels of CO2, which we're now beginning to see has an impact on violent weather or extreme weather. Now we're faced with new situations with having tornadoes, increased rainfall events, increased snowfall events, droughts. So the increase in CO2 is beginning to have an impact on weather. And with civilization being as it is today, in terms of our infrastructure, in terms of our food requirements, in terms of our energy consumption, we're entering new territory. And that's part of the concern. This is a bar chart, if you will, showing the amounts of greenhouse gases that we give off now. And it starts in 1990 and it works its way forward. And every 5 years, as you can see, the charts get taller and taller. So we are continuing to emit huge amounts of greenhouse gases into our atmosphere. And that's only part of the issue. The primary issue is that these greenhouse gases are cumulative. So when I drove down here today and I emitted my greenhouse gases, that gets added to my greenhouse gases when I had to go to Plattsburgh yesterday and to the dentist on Monday. So it's cumulative. These gases, carbon dioxide, lasts about 100 years in the atmosphere. So all of the CO2 that I've generated during my lifetime, most of it is still here in the atmosphere, and yours too, and everyone else's. So what's happening is that it's not going away. It's here. And some of the greenhouse gases have lifetimes of thousands of years, like our refrigerants in our refrigerators at home or in our air conditioners in our car. Those compounds there are very powerful greenhouse gases, and they could be around for 10,000 years. So we are changing the composition of our atmosphere in a way to absorb more energy from the sun with the unintended effects of that greenhouse gas concentrations. As part of a study of what would impact the solar energy on our planet in terms of when would it be cooling and when would it be heating, scientists have tried to look at just about everything they can, from forest fires to black soot to variations in solar energy that we receive, because the sun does go through these cycles of sunspots. And so what they did was they took everything they could think of, and on one side is the cooling effects of clouds of moisture, of water vapor, and on the other side they put all of the things they could think of that would contribute to a warming of the atmosphere. And then they add them up, and that's what they did, just like your checkbook. And when they add them up, they come out with the fact that there is a large component in the plus direction of energy being trapped in our atmosphere, and it's equivalent to like a Christmas tree bulb on every square yard of the Earth's surface, all the time, lit all the time. So it's not much, but it's there 24 hours a day, every week, every month, every year, and it's growing. So this is one attempt to try and understand those factors that could contribute to a cooling and a heating, and there's no question that when they do this calculation, it's a heating effect that we're getting, and it's greenhouse gases that are the result of that. But scientists will go anywhere to try and get data, including tidal gauges around the world. One of the things you might expect as the planet heats up is that the ocean levels will rise because of increased melting of ice. And so they went around the world collecting tidal gauge data from Newfoundland to Canada to US to Europe, and that's the chatter that you see there. Different tidal gauges showed different effects over the past century and 130 years about. But by averaging them out, you get this dark curve here, and the dark curve shows an increasing trend of heights of sea level. So you average out all those tidal gauges, and you get this increasing height of the ocean. Then in about 1990, they put up a satellite, and that's this red line up here. And that satellite, lo and behold, showed the same thing. So those tidal gauges, although they weren't intended to look at ocean level heights back in 1880, in fact, were a pretty good representation of what the ocean level was then and where it is today. And now satellite data is showing the same thing. So in the past 130 years or so, the ocean levels have gone up almost 1 foot, about 10 inches. And the rate of increase is increasing because the amount of ice melt from Antarctic, Arctic, Greenland is increasing. There's another effect there too. That is, as you warm water, it expands. So the ocean levels are rising for 2 reasons. One is, as the water warms, it expands, so the oceans, which cover 70% of our planet, take up more volume. And then also the melting of ice caps in Antarctic and Greenland is contributing fresh water to the oceans, so that's causing an increase. So you have those 2 effects that are causing this increase. So that's one of the first indicators that the climate is changing. Another one is temperature. Again, they've gone to temperature records wherever they could find them around the world, and they plotted them on this chart here. And if you average in all 120 years, I believe, data that's there, you'll get this long gradual slope here. But if you average in the data over the more recent periods, over 50 years or 30 years, you'll get these other curves here. And as this diagram shows, that the rate of increase of temperature change is increasing. So although it was fairly gradual over the past century, if you just look at the last 25 years, it is much steeper. And that reflects the total amount of greenhouse gases humans are putting into the atmosphere. So there's two effects that we can demonstrate over a long period of time that are happening today as a result of the increased levels of greenhouse gases. If you look at weather, over a period of time, you'd see almost an equal number of highs and an equal number of lows, because that's just the way weather is. It has lots of variation with it. But what they're finding now, when they plot the highs and lows, is that there's a lot more high temperature records than low temperature records. And that's what this chart shows, is that for the last several years, there have been many, many more warm days than there are cold days. And these are records now. These are not necessarily just the temperature of a day. That's not a record. These are record temperatures. So there's a lot more high temperature records than ever before. One of the tough things to try and untangle, if you will, is weather from climate. We always have weather. And weather has all kinds of extremes, and that could be kind of reflected in this first chart here. It looks like a mountaintop. And basically you have cold temperatures on one side and warm temperatures on the other. But you add greenhouse gases and you add more energy to the atmosphere, and you move that further to the right, which is this second curve. So basically what you're doing is taking weather and moving it into a more extreme area of our experience, which is more hot weather, more windy weather, more precipitation, more droughts. And so this kind of is a visual of how the increased energy, increased amount of greenhouse gases in our atmosphere is changing our weather. The Ipcc report, as the Intergovernmental Panel on Climate Change, is a UN body, and the report was written by probably 1,000 scientists from around the world, 60 or more countries. And they took at that time all the data that was available to them in the literature. They didn't develop any data. They just looked at the data that was out there and summarized it. And they came out with a conclusion that the planet is warming and it's due to man. They didn't say that it was entirely due to man. Some could be natural variation, but that man was having the biggest impact. They are in the process now of coming out with their next report. They come out with a report every 6 years. So in late 2012, early 13, we should see another report. And there's been so much research done in the last 6 years, 7 years, that there's going to be, I think, a very fundamental shift in the interpretations made, and they're going to be stronger than they were back in 2007. That's my assessment, anyhow. One of the interesting things is, and we've certainly seen it up here in the last year with Tropical Storm Irene and our lake levels, has been the increased frequency of severe weather events. In 2011, the United States had $14 billion weather extreme events. I say $1 billion in the sense of damage. And of course, that's a record. The United States has never had $1 billion damage events from weather before, but this is what we can expect. And the chart shows a gradual increase of extreme weather events. And based on the science, we expect that will continue. No guarantee, because as you notice, there are some years when there are slightly less major weather events. But in general, the slope is going up.
It looks like 2012 is going to be a rocky road, doesn't it?
Well, 2012 is still to unfold, but certainly the first 3 full months of the year, we have experienced very different weather than what we've had before. We haven't had the flooding like we did last year in Lake Champlain in May, when we broke the 180-year record, whatever it is, for height by 1.3 feet. We didn't have Hurricane Irene that dumped 10 inches of rain in Keene. And when you dump 10 inches of rain in a mountainous area, all that rain goes down into the valley and washes away infrastructure and homes. So what we can expect this year, I don't know. It will be interesting to see.
You'll be on top of it, whatever it is, Ray.
This is just a listing of significant weather events that they predict. There's no assurance that any or all of them are going to occur in a particular year, but this is what we can expect. As the atmosphere heats up, it can hold more moisture. And when it holds more moisture, that moisture will come out. And it comes out as extreme weather events. It could be rain if it's 33 degrees. It could be snow if it's 31 degrees. 2 years ago, Washington, D.C. had Snowmageddon. Well,
It sure did. Oh, yes.
The temperature was about 30 degrees, and so all that increased moisture fell as snow. Otherwise, in Hurricane Irene, Tropical Storm Irene, it came as rain. So it just depends, but warmer air holds more water, and more water has to come out because we're in a steady equilibrium with our atmosphere. So things will continue to have that kind of an effect. In addition, wind patterns change. So the Southwest, they expect to become drier. It's already dry, but last year we had those big forest fires in Arizona and New Mexico because the ground is heated up more. There's less moisture in it because it's being heated up and the moisture is being carried away. And so when it does burn, it burns hard and it burns long. So weather patterns change. We might be lucky here in New England in the sense that we will have more rainfall, but it may not come when the farmer wants it. It may come in May or in September when they want to harvest. It may not come in June and July when they want the crops to grow. So that could happen. Not necessarily will happen, but it could happen. We're going to have these extreme events, but the timing of them is going to be uncertain during the course of the growing calendar. One of the big indicators of a warming globe is the loss of ice in our glaciers. So this shows, this map of the Earth shows the glaciers around the planet. And it shows the reds are where they're shrinking and the blues are where they're growing. 90% of the glaciers on Earth are shrinking. And a few areas in Alaska, and I believe there's one in Russia, is increasing. But generally, 90% of the time, glaciers are shrinking, and that's due to increased temperatures. This is these are two photographs here. One is from about 1930, 1941, and another one is 2004. And the photographer in 2004 worked very hard to find the exact spot where that 1941 photo was taken, and the visual image is dramatic. There's been a tremendous change. This is in Alaska, so this is one end of our planet, and then this is in the United States now. This is Glacier National Park, and Glacier National Park had at one point about 100 different glaciers, and now we're down to about 25. This is one that has disappeared in the last half century. This is it today. There's no glacier left here. But then going to the other end of the planet, down to Argentina. This is the Uppsala Glacier in southern Argentina. And you can see the extent of this glacier. I believe this is somewhere around 1935. I could be off by a year or two. And this is it today. And you can see a dramatic change. So it's happening not only in Alaska and the U.S. and the tip of South America, it's happening around the globe. Glaciers are melting. For about 500 years, Europeans have been trying to go and find an easy way to the Orient for spices and other good things, porcelain. And the northern route was always blocked. By the northern route, I mean through the Arctic. And try as they might, they would send expeditions out across the Atlantic and try and find their way through the Canadian archipelago to the north of us. They couldn't do it. Many men died, probably in excess of 1,000 men died trying, and suffered amazing experiences as a result of those attempts. But it wasn't until 2007. It wasn't until 2007 that there were pathways opened through the islands in the Canadian archipelago that allowed ships to go from east to west and also from west to east through a corridor that was never open, and that's along the Siberian border. So there were two routes now, one north of us and one north of Russia, that were open for the first time in known history. Now, it may have been open a couple 100,000 years ago, but we were not around then. So this began, actually, there's a couple of shipping lines that have been brought into being by entrepreneurs who are always looking for, a new venture. And so there's one called Beluga Shipping, and they're actually now using the pathway through the Arctic to bring materials from, say, Vladivostok in Russia across to the Siberian ports to supply them rather than by rail or overland or by plane. So things are changing in the Arctic, again, as a result of climate change. One of the toughest things to do is to try and measure what happens to an ice cap. So here you have Greenland, and it's 600,000 miles of ice. How do you measure whether it's changing? Not an easy task. You can send out 200 students, and you'd still only sample a small part of this ice cap. It wasn't until they had a satellite go up in early 2002, I believe it was, that was able to use the increased gravity associated with an ice mass, and that would tug this satellite down just a little bit, and they could then measure that little bit of a drop because of the increase in gravity of the ice, and that's what you see here. And so this is called the GRACE satellite. This satellite has also been used in the Antarctic, and the Antarctic shows the same thing. There's variation within a year, there's variation within a season, but when you look at the average of the data is all pointing to a loss of ice. And again, that ties in with the increased levels of the ocean. And it ties in with the increased levels of greenhouse gases in our atmosphere. So the data is beginning to really come together and make sense. So we talked a few minutes ago, Gordy, about the Tropical Storm Irene and certain events that we had with flooding of Lake Champlain and so forth. This is in Tennessee, so we're beginning to be impacted now nationally by these extreme weather events. Tennessee, this is 2 years ago, this is in 2010. About half the state was declared a disaster area because they had up to 20 inches of rain in portions of Tennessee. Now, Irene was bad enough, but my rain gauge only had 5 inches in Chazy. I can't imagine what 20 inches would be. In any event, the Grand Ole Opry Theater in Nashville was under 6 feet of water, and it ruined a lot of instruments that they had there.
Oh, yes.
So this is an event, an extreme event. You can't absolutely say that it wouldn't have happened because of the extremes of weather, but chances are very good that it happened because of greenhouse gases. Now we're in Moscow. Moscow had its warmest summer in July of 2010 in its history. And the history in Moscow, because it's been settled a long time, goes back almost 500 years, for which they have some weather records. This is the warmest summer that they ever had during that period of time. And it was over 100 degrees in Moscow, and normally Moscow, being as far north as it is, even in the summertime, doesn't have temperatures that goes into the 80s. But here they had several days of over 100. Can't see much on this picture, but what it shows is Red Square in Moscow, and it shows the, this is during that heat wave, and it shows the smoke from burning forests around Moscow. There were probably 800 to 1,000 forest fires burning around the city, and it contributed this haze, and people were walking around with masks, and you couldn't even see across Red Square.
Right.
This is an indication of the heat event in central Russia at that point. And it's this very large dark area here centered around Moscow. Now, fortunately, that area is not heavily populated, but there were in excess of 10,000 deaths during that heat wave. And they get that by looking at the deaths over previous Julys. For the last 30, 40 years, they would look at the records of deaths and come up with a number. And then they look at the deaths that occurred during this period and say, oh, there's 10,000 more. So that seems to be correlating with the increased temperatures. The previous big heat wave was in southern France, Western Europe, Western Germany, and that was in 2003. And the excess deaths from that heat wave were on the order of 30 to 40,000 deaths. So heat kills. It kills generally older people who don't have air conditioning, who may have asthma problems or other health problems. So heat kills. Cold kills too. And but that's what happened in Eastern Europe this year. There were quite a few deaths as a result of a cold wave that came out of the Arctic. So you can't necessarily say that heat is good or cold is good. In extreme, both cause damage. This is Pakistan, and Afghanistan is off to the side here. A year and a half ago, Pakistan had 20-some odd inches of rain fall in its northern mountainous region. Now, frequently the planet can handle extreme events. But if you're also doing a lot of logging, illegal or otherwise, there's nothing to hold back the soil. So even though our Keene Valley was heavily forested, we still had an extreme event because of the 10 inches of rain that fell there. But if you're in Afghanistan where you've denuded the mountains and you get 20 inches of rain or 20 plus inches, a lot more damage can occur. And as a result, they lost tens of thousands of bridges and set their infrastructure back many, many years. And it's going to be a long time before they recover their infrastructure as a result of this significant weather event. This shows the Indus River in Pakistan. Normally it's about a half a mile wide. Here it's about 18 miles wide during the peak of the flood. Let's go to South America. This is the Rio Negro, which is a major tributary of the Amazon River. And as you can see, it's dry. There's basically no water in it. It's hard to see, but there is a bridge in the background that is very high above the river. And obviously there's no water under that bridge at this point in time. But this is the second drought in 5 years in the Amazon basin. In and of itself, okay, you have a drought, but what happens to the forest, to a rainforest, when it's in a drought like this, is that billions of trees die. They don't have the root structure, there's not the soil in the ground to keep them alive, and so better than 1 billion trees died in that event. This is 1.5 years ago. Well, they called it a once-in-a-century drought. But the odd thing is that there was another drought 5 years before that was also a once-in-a-century drought. And another 1 billion trees died. So what you have normally is these trees are taking in CO2 from the air, keeping the levels down to some extent, incorporating it into their fiber, into their leaves and tissues and so forth. Now what happens when you have these couple of billion trees dead is now they're releasing this carbon dioxide that they've incorporated into the atmosphere. So you're getting a positive feedback effect. So you're adding more CO2 to the air than you normally would because of these trees that are now decomposing. So this is of concern, deep concern. The last few years, this is in 2010, last few years have shown a lot of hurricane activity. And they're not necessarily more hurricanes. The data isn't really fully clear yet that we will get more hurricanes. But the data seems to be clear that we're getting stronger hurricanes. So these are 2 hurricanes, and it's kind of a beautiful picture, again, from our satellites. It's a beautiful picture in a sense of form and action and energy. Unfortunately, these were not over land, and so there was, to my knowledge, no damage done by these 2 particular hurricanes. But both of them are Category 4 hurricanes, and you only go up to Category 5. And they had wind speeds between 135 and 140 miles an hour. A lot of energy, a lot of things taking place in our atmosphere. Los Angeles set its all-time high record in the fall of 2010 with 116 degrees. And not to be outdone, North Carolina in the fall of 2010 had up to 20 inches of rain fall on its eastern seaboard side of it. And they are used to heavy rainfall, but this was a record rainfall. And of course, then you have all kinds of problems with, attendant problems with what happens with all of that water. You have a lot of hog farms, you have chicken farms, you have manure pits, and so a lot of that excess rain then causes a collapse of this infrastructure, and so all of that pollution gets dumped into either Chesapeake Bay or into the Atlantic. So adverse things begin to happen as a result of these extreme events. This was in October 2010, and this is the largest storm, non-tropical, so it didn't originate over ocean, that the weather forecasters had ever seen. It covers about 1/3 of the United States. In the center part of the eye, up here over Michigan, it had the lowest pressure recording ever made in the continental U.S. And then it did spawn some tornadoes and some hailstorms, but it just was an example of an enormous storm happening over land and probably caused by increased land temperatures. Again, you can't say exactly that storm is a result of climate change, but it is weather that is extreme. And this is where Mayor Bloomberg got a black eye in December of 2010 when the New York City got hammered by a snowstorm, and they weren't ready, and the streets were impassable for 10 days or whatever it was. And so this is the storm. It's now blown offshore, but you can see the white on the ground from the 20 or so inches of snowfall that hit the East Coast. This is January now of 2011. This is now in Australia. Australia had rain for a couple of weeks. Normally it's fairly dry. This is in northeast Australia. In Australia, there was an area underwater equivalent in size to France and Germany combined. It was an enormous chunk of Australian territory underwater. This was caused by, not by a typhoon, but by just one of their tropical storms. I included this because it's a coal pit in Australia, nearby to the area that we just looked at. And Australia has a lot of coal. And of course, China is fairly close to Australia. So Australia sells a lot of coal to China. And of course, coal is one of the primary sources of carbon dioxide in our atmosphere. And so I thought this was kind of an interesting picture showing what happens as a result of extreme weather. That coal pit is underwater and was underwater for a long time caused by that event in northeast Australia. 2010 set 19 all-time high temperature records on the planet. It included a country like Finland, which had the highest recorded temperature it ever had. Now, Finland lies 600 miles to the north of us, but it recorded a temperature of 99 degrees. And so it's not just your tropical countries that are experiencing this warmth. It's also some other countries on either side of the tropical areas. Afghanistan, check that. Pakistan had the highest temperature it ever recorded in Pakistan. It was 128.3 degrees, I believe it is. Not only is that temperature a record for Pakistan, but it's a record for Asia, the continent of Asia. So we are setting new temperature records around the world. This is a typhoon. Now, typhoon is south of the equator. Hurricanes are generally north of the equator. Same idea, lots of energy packed into circular storms. This is Typhoon Yasi that hit Australia, and it was an enormous storm. You can kind of get a sense out of the size of it here. And it hit northeast Australia and did a fair amount of damage, but that area of Australia is not heavily populated. So it didn't cause a lot of damage to infrastructure, and as you can see here, boats and homes. It was mostly to the native, to the natural territory, trees and so forth. This is one of the big storms that hit the U.S. a year ago in February. And it covered about half the United States, maybe a little bit more than half the United States. And this had the snowfalls in Washington and in the Midwest and Chicago. It was an enormous snowfall, and you can just get a sense of it from how much of the United States is covered by this enormous storm. This is last March. This is in Thailand. Now, this peninsula in Thailand around the town or city of Phuket is a magnet for people around the world that go there to experience the beaches, the scuba diving, the swimming, the nice weather. Normally they get a couple of inches of rain per month in March. Here they got 18 inches in 3 days. So it caused extensive flooding, but it just is an example of what happens to a climate that's warming, that can absorb and hold a lot more water. And then when these conditions are right, that water then comes down in a big rush. This sequence here is part of a series that has a lot of tragedy associated with it. And it started off basically in March with the sea surface temperatures in the Gulf of Mexico above normal. And that's the dark orange, yellow color there. The sea surface temperatures were higher than normal. Again, warmer water, warmer air, more moisture in the air. And what happened was that it began to rain, because the winds come up through Texas and Louisiana into the midsection of the country. It began to rain, and in rain it did. This is this weather map here from a weather service shows about 16 inches of rain in Missouri. Now, Missouri, as you know, is on the Mississippi River, and it also is got on the north side, it's got the Missouri River. So now we're beginning to saturate the ground and fill up our local rivers there, and it didn't stop. This is in April, May, and this is what impacted us with our high lake levels last May. And the weather patterns came up through New England, and you can see the darker color here is much more precipitation. And it covered the Ohio River Valley to the east of the Mississippi River. So now you have the Missouri River, you have the Mississippi River, and you have the Ohio River all flowing into central Illinois, or the west coast of Illinois. And it caused the Army Corps of Engineers to do something they don't like to do. They broke the levees outside of one of the cities there in, I believe it was Missouri, not Illinois. And what they did was they had to take pressure off of the levees because they felt that if the levees broke by, say, St. Louis, that would cause enormous damage. So they flooded enormous amounts of farmland with 6 feet or more of water to take the pressure off. And it worked, but it's not something they like to do. And they've been trying for 70 years to contain the Mississippi River, and generally they've been successful. But with the extreme events we're experiencing now, they run into this kind of a problem. This is the state of Minnesota, and I only included that because it shows a storm moving across the whole state, 300 plus miles, whatever it is, the distance. And the shadows, they were able to measure the height of the cloud, and the clouds went up to about 40,000 feet. So this was a storm. You can't say it was due to any particular event, but it certainly was one of the most strong in their recent history. And it had hailstones on the order of 3 inches across. So I don't know what your car would have looked like. But mine,
My poor little car, are you kidding?
so,
Have you ever owned a car that was through a hailstorm?
no.
We owned a used car several years ago that had been through a hailstorm in Tennessee with tiny little pieces of hail. And from 10 feet away, you'd never know it. But when you get up close, you saw 40 million tiny pock marks.
Yeah.
And at first, it was beyond what I could understand.
What had happened? Huh?
And then somebody like you, far brighter than I, said, I've seen that, that's a hailstorm. And I bought a brand new truck I didn't realize it, but I took it to a local body shop for some minor repair. And the guy said, do you realize that they're tiny little? I said, it's a brand new truck. It's never been through a hailstorm. It was on a truck coming here from somewhere, and that's where that happened.
Okay.
So
Yes.
there's more there than meets the eye.
Right.
Unbelievable.
I started off a few slides back with the higher sea surface temperatures in the Gulf of Mexico and the storms and the moisture that came off of that. This is a couple of weeks later when we had that burst of tornadoes going through the southern part of the United States in the southeast. And what had happened is that all of this energy from the warm water, all of this moisture met cold air coming out of Canada, and then we had the El Nino effect coming in from the Pacific, and it all came together and created a lot of wind shear. This may not be easy to see, but there are big storm cells beginning to form over Alabama and Georgia, Mississippi, Alabama, and Georgia. And we know what happened as a result of that. This is a satellite photo of Tuscaloosa area, Alabama. And you can see on the photograph there the actual tracks from outer space of these tornadoes. These were very strong, intense tornadoes. They covered a lot of ground area, and you can see 4 tracks there in a row going parallel to each other to the northeast. And of course, the This is from outer space, but if you look at on the ground level,
Oh,
the
yeah.
damage was awful. There was a tremendous loss of life. And this is Joplin, Missouri, which really got hammered. And this was I think a force 4 tornado. I don't think it was a 5, but it destroyed 10,000 homes and a hospital. And the winds were so strong that it not only took the leaves off the trees and the small twigs off the branches and the small branches off the big branches, it stripped the bark off the trees. So it was an enormously powerful storm. And it's going to take them a while to recover from this, and they are beginning to. This is Southern Africa. This is one of the driest nations on Earth. And this is Namibia, which is on the Atlantic Ocean. And they get a couple of inches of rain a year. Well, they got 3 inches in a week here. And for them, that caused a lot of flooding because they were not prepared for it. And also the countryside is not prepared for it because there's nothing to hold it back. So these extreme events are occurring on all of the continents. And it doesn't have to be 20 inches of rain. It could be 3 inches of rain. But it's just different than has been their history before that. And then, of course, the forest fires, as we talked about earlier, Gordy,
What a shot. Wow.
in New Mexico and Arizona. And the size of the Adirondack Park was basically consumed by fire, by wildfires in that area there. I kind of like this picture here because it's a photomicrograph. And what you're looking at there are pollen grains. So what happens in a moister world is that you get more plant growth and you get some of the plants that you don't like that causes allergies. And so there's a lot more pollen in the air. Ragweed, for instance, loves water, loves warmer air, but it hurts people that have asthma or any kind of respiratory problems. And so this is an indication of just what these pollen particles look like and what we can expect to see more of in the future. And this is some research being done to try and understand that aspect of increased rainfall and increased temperatures and the impact of climate on health. And this is our friend, Lake Champlain. And this was a photo taken from the Vermont side looking toward the Adirondacks in September 1st, thereabouts, of 2011. And it shows an angry looking Lake Champlain. And what happened last year was a convergence of events. In May, we had the very high water that broke all records. And it began to drop as the season progressed, but it never got as low as it normally gets. And then you have a tremendous rainfall like we had from Tropical Storm Irene. And now you have a higher lake with a lot more water in it, and it caused a lot of damage along the seashore. And this is the Boquete River. Normally you can walk across that in September, and I've done it with my grandchildren, and not get your knees wet. This is one full angry river with all of the rainfall coming from Keene and elsewhere that caused a lot of damage. This is the Mohawk River, which also experienced a lot of flooding, and both ends of that bridge were unavailable to traffic. And another photograph showing multiple hurricanes in the Atlantic, all at the same time. Fortunately, the U.S. was very fortunate last year. We only had tropical storms hit us. We didn't have any severe hurricanes that made landfall. So the damage caused by winds was minimal, although we did get the water. And another one showing several more hurricanes last fall. This is last September 2011. One of the interesting things, at least to me, is what students do and the research that they do and what they come up with. In the Arctic, there's two populations of whales, one by Greenland and one by Alaska. And because the Arctic has always been frozen, they've always been separate populations. Well, what this shows is that students had tagged a whale from Greenland tagged the whale from Alaska and then followed by GPS their migration. And what this shows is the two trails, the red and the yellow, coming together for probably the first time in who knows how long.
Yeah, isn't that, who would ever guess anybody would do that kind of research?
Yeah.
I love it. That's great.
There's no indication that the whales knew each other was present, but their tracks did cross. So it's, again, it's just
That's brilliant.
an
That's
interesting piece of
just
work.
beautiful. I love it.
And then last fall, there were some very significant typhoons off of northern Philippines, dumping enormous amounts of rain. Again, we're in the 20-inch category here. And they kept on going towards Southeast Asia, toward Vietnam, Cambodia, Thailand. And this map shows the course of the typhoons and also the rainfall amounts. But this is a shrine in Thailand, and about 1/4 of Thailand was covered by water. Now, normally Thailand is an exporter of rice to Southeast Asia. They are the rice basket, if you will. And they lost a very significant portion of their rice crop, which then has attendant issues in terms of population, food shortages, and so forth. So this is, again, an unintended effect of significant amounts of rainfall.
A lot of information to soak up, so let's pause for just a moment and get back to it.
Great. And
Oh, wait a minute. Okay, we're underway again. We just took a deep breath, and we got about 10 more minutes to cover the rest of the slides. I love it.
we're almost finished, Gordy.
Oh, we're on the home stretch,
And
Doc.
again, I just wanted to show you a more recent weather event that was very unusual, and this was in end of October 2011, just 4 or 5 months ago, when we had that freak snowstorm. It didn't hit us in the North Country, but it hit the below Albany over toward Connecticut, Massachusetts, and so forth. And the leaves were still on the trees. There was definitely a strong wind, not a hurricane, but strong winds. And then there was 6 inches or more of a very wet snow. So again, you had a convergence of different things coming together. And there were millions of people without power.
Oh, yes.
There were people without power for up to 10 days in parts of Connecticut. So this is just a satellite photo showing the streak of white across the center northeast part of the United States. Also in November of this year, this is off the west coast of Alaska, and it shows a huge storm coming from Siberia, and it prevented some cities from getting their annual oil supplies there. And so by the time the storm was over and so forth, the seas froze. We had to hire a Russian ship to transport oil. I think it was to Nome, and there had to be an icebreaker in front of it in order to deliver that oil to one of our cities in Alaska. So strange things are happening all over. Great Lakes ice cover. This is data over the last 30, 40 years. Lots of weather. Some years it's more than others, but if you look at the long-term trend is down. Lake Champlain freeze updates. Each little star on that chart there shows a year when the Lake Champlain did not freeze over. That's at its widest part. Obviously in the bays it freezes over every year, but at the widest part. In the almost 200 years worth of data there, it hasn't frozen over about 35 times. And as you can see, most of the times it has not frozen over has been in the last 30, 40 years. This was a photograph released by NASA in January of 2012. And this is one of the concerns that climate scientists have. And this is in Antarctica and shows an ice shelf with a crack in it that's breaking off. And it's in the process of being separated from a glacier. It is, it's about 200 square miles, so it's an enormous ice cube. And it will be, it hasn't completely freed itself from the glacier yet, to my knowledge. But when it is, because that crack is there and it's 180 feet wide right now, that crack, it will be circulating in the southern seas,
That
Pacific
will
and
be
Atlantic
interesting, won't it?
for years before it
Wow.
passed. So this was in January. And these are organizations that were used by me to come up with these slides. And it includes NOAA, which is the Oceanographic Administration, and then NASA, of course. GISS is the Goddard Institute of Space Studies. That's at Columbia University in New York, where one climate scientist, James Hansen, is very prominent and has published a lot of papers. NSIDC is the National Snow and Ice Data Center, so we do actually have an organization that collects data on snow and ice all around the world, but primarily the U.S. NAS is the National Academy of Sciences, which was organized by Congress over 100 years ago, and it's intended as a research arm of Congress, and they are the top scientific agency in the United States. NYSERDA is New York State Energy Research Development Authority, and
He's got them all down, Pat. I would labor over that one for weeks, Raymond.
the National Weather Service, NWS, and then the World Meteorological Organization have provided some of the information here, and of course Wikipedia. Wikipedia provided the Keeling curve.
Which is actually gaining more credence as time goes on. It was kind of an interesting development at first, and you couldn't trust very many things you read on Wikipedia, but you notice
It's getting better.
It's getting a little more erudite than it
Yeah.
was before, and you could trust more things. You still have to be careful where you pluck your information from. That's why we can count on this today. This is wonderful.
Well, I want to end it on a positive note, and it'll only take me a minute, and that is there are countries and there are cities around the world that are doing a lot to try and reduce their carbon footprint. Denmark is embarked on a
Yes, they
program to
are.
be energy neutral, fossil fuel neutral. Sweden is doing the same thing. They have a city called Vaxjo, which is the greenest in Europe. We have Seattle that also is doing a lot to reduce the carbon footprint of its activities. So there are good things going on. We have that windmill farm up here, which is generating a lot of power. It's not favored by everybody, but it still is generating a lot of power that
You know,
we all like to use.
Calvin and I followed it with Hometown Cable from the very beginning, watching those towers grow and taking pictures of them to the point where his neck was crooked by the time they get that nacelle on the top.
Yeah,
Amazing. And we can all do our part.
we can.
I mean, as simple as it sounds, we can all do our part.
Yes, we can.
That's why I drive that hybrid car out there. You were just mentioning a couple of these books to the public as we can. Just give me about 20 seconds on each one of these.
This is a local author. His name is Jerry Jenkins, and this was published in 2010. And its focus is on the Adirondack Park and how we can take steps to reduce our carbon footprint, our fossil carbon footprint.
Okay.
And this is Bill McKibben, who is a well-known author. He lives in the Adirondacks on the south end in St. Johnsburg. This is a book that summarizes a lot of the current data. And this gentleman is Kurt Steger from Paul Smith's College. He's a professor there. And this was just published less than a year ago. And again, it gives a very interesting summary of climate in the Adirondacks.
Dr. Ray Johnson, it is a pleasure. Let me shake your hand.
Thank you, buddy.
Are you available to do presentations? If
Yes.
somebody's watching now, how would they get a hold of you, Ray?
On my website, icsusa.org, they can send an email and I will get it, and I will try and address whatever their interest is.
I'm so delighted that we did this. I love to collect information. It takes my poor old brain a while to process all of this. And it's like saying, be careful, folks, because an asteroid is coming, and it probably won't be here for another 1,000 or 1,200 years, but watch out, it's going to be close. It's a process that's happening, and it sounds to me like it's inevitable. And I'm not sure that we'll do enough in the rest of my lifetime to slow things down.
I personally think that if we have the right policies in place, we could stabilize the climate in the next decade or 2 decades.
Wouldn't that be nice?
But that doesn't mean that we're going to go back to the way it was in the 1950s. We would stabilize it at about its current level, maybe a little bit more extreme weather. But it doesn't have to necessarily be totally negative.
I'd like to end on that note. Best of everything to you,
Thank you.
my friend. Thank you to our viewers for all of your comments and suggestions. One of them brought us right here today, and I love it. Thank you also for any of your ideas about this hometown cable program, the one that we do here called Our Little Corner, and all the other events that Calvin covers in the course of, for him, almost an entire lifetime since 1983, if you can believe that. And like I always say at the end, who knows where we're going to be next time for Our Little Corner.